Welcome to chapter 12. We're going to just jump into section 2. As usual, we're going to skip that section 1 insight. Chapter 12 is all about equilibrium. So we spent a lot of the last couple of chapters talking about whether a reaction would go forward spontaneously and then how fast would it go. And now we're going to think about the forward and reverse reactions of equilibrium reactions. So what is meant by equilibrium? Well, to start us off, right, we're saying that the net rate is 0. All right, so the reaction has proceeded and now we're not getting any overall change. So to start off with something kind of something a little bit simple to study what a dynamic equilibrium looks like. Think about these glasses filled with water. All right, on the left in each picture, you have a glass that has a cover on it. And you see that level of water stays the same, as you might expect. Then on the right, you have your uncovered glass, and over time, that water is evaporating. So this shows us something, that water sitting out at room temperature is evaporating. So what is going on then inside of the covered glass? Well, when you first put the water into the covered glass, you have evaporation occurring, right? You have this forward reaction of H2O liquid going to H2O gas. And so that rate of evaporation with the lid on it is actually going to remain constant. At the beginning, when there is no water vapor in the glass, the rate of the reverse reaction is 0. There isn't any H2O gas to condense. But as you start to make H2O gas and those molecules are bouncing around all over the inside of that container, but it's covered so they can't escape, they will occasionally collide with the surface of the water, and sometimes if they lose enough energy, they will condense back into the liquid form. So the reaction is proceeding forward at a rate that is higher than reverse until you get to this point where the rates converge. This is once you reach equilibrium, and now you've got what's the word? It's a static amount, not static, this is dynamic. You have a certain amount in the liquid phase, a certain amount in the gas phase, and you're not getting any net change. You have the same number of liquid molecules evaporating as you do gas molecules condensing. And that's called a dynamic equilibrium. It's not stopped. It's not just liquid molecules on the bottom, gas on the top, and everything stays exactly the same. It's just that there's not a net change in amount. You will continue to have evaporation and condensation occurring at this equilibrium. Right? And so that is our dynamic equilibrium. Now, we're going to apply this to a chemical equation, right? And we're going to start looking at a reaction. In a reaction, right, we're going to start off with reactants, and we're going to move forward to products. But some chemical reactions have a significant equilibrium, where products go in the reverse direction and reform reactants. When we compare the concentrations, right, in the beginning, it's all reactants, no products. And the rate of the reaction is at its greatest. As you start to lose reactants, the rate starts to slow down as you start to form products. And as you start to form products, the rate of the reverse reaction begins to increase. Equilibrium is when these two level out. All right, so the chemical system reaches equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. All right, it's an important definition for equilibrium. Now, mathematically, what does that tell us? And I'm very sorry about these weird boxes. I don't think you'll see them if you open this up on PowerPoint. But we could write a rate reaction for the forward and the reverse, right? So we know that rate forward equals some sort of concentration, some sort of rate constant for the reactants, right? The disappearance of the reactants. Then there is going to be a rate that is reversed where you will have a rate constant for the reverse, and that will be based on the concentration of the products. Now, at equilibrium, right? At equilibrium, the rate forward will equal the rate of the reverse. So we can rewrite this, right? We can plug in for the rates. K forward times reactants equals K reverse times the concentration of products. And if we rearrange this, and we're just going to keep moving along here, K forward over K reverse would equal products over reactants. So if we maintain our temperature here, this is a constant divided by a constant, so it gives us a new constant, right? And that is called our equilibrium constant if we're at equilibrium, right? This will be a new constant here. And in fact, let me erase that. We're going to keep talking about this. So how can we write this for specific reactions? Well, first, what we want to do is we want to recognize this as this relationship's called a mass-action relationship. We are going to be interested in both the starting materials and products and their stoichiometric coefficients. Now, let's write something out together. This mass action statement is Q, so we'll talk about Q in just a moment, is going to be the concentration of your products raised to the stoichiometric coefficient divided by your starting materials raised to their individual coefficients. And this is your mass action expression. Now, Q is called a reaction quotient. Q is the reaction quotient. If your concentrations are equilibrium concentrations, then Q equals K at equilibrium, right? And you can rewrite that expression, and then you know that your equilibrium, that your concentrations are the equilibrium concentrations. We're going to talk about what that means mathematically in a minute, but first let's get a little bit of practice. We can write an equilibrium expression for any balanced equation. For this, K would equal the concentration of SO3 squared divided by the concentration of SO2 squared times the concentration of O2. All right, relatively easy there. Something else to be aware of is aqueous solutions are often dealt with in terms of concentration, and sometimes gases are as well. But sometimes it's easier to discuss gases using their partial pressures. And so an equilibrium constant that uses pressures, right? So that'll be partial pressures of the products over the partial pressures of the reactants. And Kp and Kc are related, but they're not necessarily the same. So up here, this was technically Kc. Most of the time we're dealing with molarity, and so that C will often be left off. But if you see Kc, it's talking about equilibrium using concentration. They can be equivalent, but they aren't necessarily so. Kp equals Kc times RT, so the gas law constant times temperature, raised to the change in moles of a gas. So if on the starting material side and on the product side you have the same number of moles of gas, Kp and Kc will equal each other, right? If this up here is a 0. But if there is a change in moles of gas, like for instance in this problem right here, there's 3 moles of gas on the starting material side and only 2 on the product side. So Kp and Kc wouldn't be equivalent, but you could figure them out pretty easily. R is that gas law constant if you know the temperature. And then of course the change in gas would be -1. Or it would be, yes, -1, final minus initial. Another thing that's really important to keep in mind when writing equilibrium expressions is homogeneous versus heterogeneous equilibrium issues. All right, so homogeneous equilibria, reactants and products are all in the same phase, they're all aqueous, they're all gas. But there are going to be heterogeneous equilibria that we're interested in that have solids and liquids mixed in. And you need to know how to deal with solids and liquids. You leave them out. And think about it. The concentration of a solid isn't going to change, right? As you get less of the solid, the volume is also going to go down. So the concentration, it doesn't make sense to talk about them that way. So you just leave those out. They don't affect the equilibrium expression. So for instance, if we were going to write the equilibrium expression of the breakdown of calcium carbonate into calcium oxide and CO2, the equilibrium expression would just be the concentration, oh goodness, being a little messy, of CO2. Now, what if you don't have anything on the product side that you're going to include? Well, that's okay. You would, oh, I'm sorry. Okay, you would leave it out. I have an example here. Let's move this up where it belongs. That goes with this problem. And then let's write the one for this guy. All right, so this one would be K equals, now on the product side, we only have a solid, so there would be nothing but a 1 in the numerator. And then on the reactant side, we would have the calcium 2+ ion, and we would be multiplying that by the hydroxide ion, which would be raised to the 2nd power. All right, so you definitely want to make sure you practice. You can write equilibrium expressions. When we think about what K means, this equilibrium constant, it's nice to know a little bit about what the value is telling us. And K can be huge and K can be tiny. There are examples where K can be as small as 10 to the negative 99th or as large as 10 to the 99th power, right? They can be very large, very small. And knowing what the size of K is can tell you if the reaction favors the products, favors the reactants, or has a bunch of both. So if K is greater than 1, right, that means that your numerator is bigger. That means we are favoring products. If K is less than 1, then we are favoring reactants, right? That means the denominator is larger. If K is about equal to 1, you have significant amounts of both. Okay, so that's what just knowing K can tell us. And it allows us to also predict some behavior. So if we are looking at these two equations, and I'm not sure, oh no, it matches, okay. We're looking at the precipitation of calcium with hydroxide and magnesium with hydroxide. They both make a precipitate. right? Calcium hydroxide, magnesium hydroxide. And they both have a K that is greater than 1. So both of these individual reactions favor products. But if you had calcium and magnesium and hydroxide around, which one would be precipitated more? Like, which one would be preferred? Well, K for the magnesium reaction here is bigger than K for the calcium precipitation. So that means this one's going faster in the forward direction. It favors the forward direction more. And so if we had to guess which ion is more likely to precipitate hydroxide, it would be magnesium because of that K value. All right, so K values can give us some information. If we are manipulating our equilibrium expressions, it's usually easiest just to rewrite the expression. But if we look at this example over here, right, so we have just our basic equilibrium expression that we've already written in our notes, right? K is products over reactants. Well, if you flip your reaction around and you are looking at now what was the reverse reaction, then you see that your numerator and denominator have switched places. So when you reverse an equation, K of the reverse reaction is just going to be 1 over K. If you wind up adjusting the stoichiometry, it's not that simple. You really just need to rewrite the whole equation. If you adjust the stoichiometry, it's going to adjust each exponent. All right, so let's just jump into an example here so we can kind of see what we're talking about. So we're looking at the reaction that forms ammonia here. And first, let's practice just writing the equilibrium for the reaction as written. K is the concentration of NH3 squared divided by the concentration of N2 divided by H2 cubed. Now the reverse reaction is just going to be the flip of that. It would be N2 times H2 cubed, all divided by ammonia squared. If we wanted to write it with all of the coefficients in the equation halved, we would just adjust all of our exponents. NH3, instead of being 2, right? So we're multiplying this whole thing by 1/2. That would just be to the 1, right? And then on the bottom, N2 was 1, so it's going to be raised to the 1/2. And H2 was 3, so it's going to be raised to the 3/2. Right? You just want to make sure that however you manipulate that reaction, that you reflect that in the equilibrium expression. The equilibrium expression will be different if you flip it around or you change the stoichiometry. It is sensitive to those manipulations. The last thing that we're going to say in this video, I just want to make clear, or the units, which means we're skipping series of reactions, right? So we just write that in here. You can skip the equilibrium constants for series of reactions. You're not going to be responsible for that. So you're not going to need to do that problem. And the last thing that we'll mention in this video is units. K is dimensionless. You have molarity on top, you have molarity on bottom. Molarity is all going to cancel each other out. And so for this kind of a problem, it's one of the few times where I'll ask you to calculate something and it just doesn't have units. Right, so we want to make sure that we pick up on that. Rate constants, units are important. Equilibrium constants, unitless. All right, we'll get into equilibrium concentrations in part